Imagine waking up in the middle of the night to heavy rain. By morning, the river has overflowed. Homes are flooded, roads are destroyed, entire communities are underwater. People often say the flood came unexpectedly. But for engineers, floods are not surprises. A poorly designed culvert, bridge, or a dam can mean the difference between safety and disaster. So in this video, I will show you how engineers predict floods before they happen using professional hydrological methods. These are the same methods used by consultants when designing dams, bridges, spillways, and stormwater drainage systems. So by the end of this video, you will understand how rainfall becomes river runoff, how to estimate extreme floods, and how engineers determine the 100-year flood. But first, we need to understand why predicting floods is critical. Floods can destroy infrastructure, homes, and lives. So engineers must account for extreme events when designing bridges, culverts, spillways, and stormwater drains. Because underestimating floods will always lead to collapsed bridges, overflowing roads, dams overtopping, and even massive economic losses. So predicting floods is a core part of hydrology, the science of water movement in the environment. So when we're predicting floods, we are catering for uncertainties for our infrastructures. So there are various steps that we are going to follow to ensure that floods are predicted well. The first one is to collect rainfall data. So the first step, like I said, is rainfall data collection. Now rainfall data is a very crucial input because without rainfall, it's very hard for a stream or a river to flood. So rainfall data can be obtained from various sources, including local weather stations, satellite rainfall data sets, historical hydrological databases, and rainfall intensity and duration control how much water enters rivers and streams. For instance, TRMM, which stands for Tropical Rainfall Measuring Mission, provides long-term rainfall records used by engineers worldwide. There are also some other various data sites which provide good rainfall data or rainfall information that we can use for our system analysis. Now, once we have our rainfall data collected, the next step is to analyze the watershed. The watershed or the catchment is just the land or the area draining into a river or a stream. All that part of the land which collects or drains water into the river or a stream is a watershed. The major factors that we look at when doing catchment analysis is catchment area. We have to understand how big is the size of the catchment, because the bigger the size of the catchment, the more the runoff they are going to collect, or the more runoff is going to enter into our stream or the river. At the same time, you also have to understand the topography or the slope of the catchment. A catchment with a steep slope will always have fast floods or rapid runoff into the stream, and the reverse is true, which means the catchment with a gentle slope, the floods will take long to enter into the river. We also have to look at the soil type. This has a big impact on the catchment. There are various hydrological soil groups, but the major factor we look at is the infiltration rate. A soil with higher infiltration rate will always have slow runoff, while a soil with slow infiltration rate will always have rapid runoff. For example, it's a clay soil, because when water lands onto the soil, less will be absorbed or taken down, and more of it will be taken as a runoff. Then we shall also look at the land cover, because the type of land cover has an influence on the watershed, or directly attached to the kind of flooding the area can undergo through. So when the land is covered by water, urbanization, forestry, or agriculture, they have an impact on the flooding which the catchment will undergo through. So why does this matter? Because urban areas will always have fast runoff, therefore higher peak flows, whereas forested areas will always have slower runoff, therefore lower peak flows. So these factors directly affect flood magnitude. Now the third step is to estimate the runoff. because not all rainfall becomes river flow. Some water is lost through infiltration into the soil, evaporation, or vegetation interception. So what engineers do, they use models like SCS scarf number method or hot-end infiltration model to help us to estimate the runoff. Now these models convert rainfall into effective runoff. So that is what enters into the rivers or the streams. So once that is done, we go to the next step, which is to perform flood frequency analysis. Once river flow data is available, engineers now perform flood frequency analysis. Now the purpose of the flood frequency analysis is to estimate the extreme events like a 100-year flood, 50-year event, or even 100-year events, because this is what we are going to use as an input for designing the key hydraulic structures. So a 100-year flood has a 1 probability of occurring in any year. Probability distributions like Gamble distribution help us model these extreme events. So once that is done, we go to the next step, which is to develop flood hydrographs. Engineers convert runoff into a flood hydrograph. A flood hydrograph is a graph showing river discharge over time. Now there are various tools and methods that are used, like a unit hydrograph method or other various medical hydrologic models. All of them, they help us determine the peak discharge, the time of the flood, and the flood duration. Now these are very crucial inputs that we are going to use for our sizing. Like the peak discharge is critical for sizing the bridges, culverts, and spillways. So the last step is to apply all this that we have done to our design. So flood estimates are used to design bridge openings, culverts, dams, and spillways, and stormwater drainage systems. For example, a dam spillway must safely pass the designed flood discharge to prevent overtopping and to safeguard the lives and the property which are on the downstream side of the dam. So accurate flood prediction ensures resilient infrastructure and community safety. So the major takeaways from this video is flood prediction is not guesswork. It combines rainfall analysis, watershed characteristics, runoff modeling, and statistical extreme value analysis. And using these methods, engineers anticipate floods and protect lives, infrastructure, and investments. If you want to learn more about practical engineering workflows, please subscribe to the channel.